you very much for inviting me. It's a shame not to be there with you in person, though I live in North Somerset and work in Exeter, so it's a little bit of a distance away. So um, today I'm going to give a bit of an introduction to astronomy, and then talk about telescopes and imaging and what we can observe in the sky, and then finishing up with computing and astronomy research. And hopefully that'll kind of give you a little bit of an overview of astronomy, and then put some of the computing in astronomy research into context. Just starting with a little bit about me, I've kind of had sort of been in and out of astronomy over quite a few decades. So I first became seriously interested in astronomy way back in 1984. And you can see the kind of book on the top right that got me started. Then I did a degree in astronomy and physics at UCL in the 1990s, uh, followed by moving into a career in IT. I then, whilst working, did a part-time maths degree with the Open University, and then went part-time so I could do a part-time PhD at University of Exeter. And I'm very fortunate to be employed as a postdoctoral research fellow at the University of Exeter, where I do research into star formation and young stars. I'm also very much an amateur astronomer. The sort of real key difference is amateurs don't get paid, but do it just because we like it, whereas professionals actually get paid, which is more than nice to have. I've been involved with the British Astronomical Association Variable Star Section since about 2001, but also do just sort of sketching of deep sky objects. Down the bottom left, you can see that's a picture of my observatory with my telescope. We actually just use visually with my kind of eye at the moment. I do things like sketch Mars and deep sky objects with things like clusters, nebulae, and galaxies. I also have a smart telescope, and I'll be talking a bit more about those later. And that's this one in sort of to the right. That's what's called a dwarf 3, and they're very good for deep sky imaging. So that's the sort of clusters, nebulae, and galaxies. So moving on to the introduction to astronomy, I'll just start off with a couple of things just to put in sort of context for sort of what we're going to be talking about in astronomy as a whole. So what we see with light is the visible spectrum, but that's just one small part of the electromagnetic spectrum. The electromagnetic spectrum is sort of visible light. You have blue is shorter wavelength and red is longer wavelength, but it's only about twice the length of the blue wavelength. If you go to even longer wavelengths, you get the infrared, microwave, and radio. If you go shorter than blue, you have ultraviolet, X-rays, and gamma rays. And astronomers use all of these, some of them from the Earth and some using space-based observatories. Also, just to give a scale of size and distance. So very quickly, kilometers and meters become a bit meaningless. So one of the smallest scales, which is kind of commonly used in astronomy, is called the astronomical unit. And that's the average distance between the Earth and the Sun, which is about 150 million kilometers and is termed as 1 AU. Another very common length measurement is the light year, and that's how far light travels in 1 year, traveling at 300,000 kilometers per second. That translates to 9.5 trillion kilometers in a year, which is 9.5 thousand million kilometers. However, astronomers, professional astronomers, tend to use the parsec, and that's because it's related to how we measure the distance to objects using trigonometry and parallax. And that's close to the light year. It's actually 3.26 light years. So they're very sort of similar. It's just professional astronomers tend to work in parsecs. So what I'm going to do is sort of start from the nearby solar system and then kind of move off into more distant objects. So we have in our solar system, we have the sun at the center, which is just a star, a pretty typical ordinary star. Then we have the four inner planets, which are rocky worlds, Mercury, Venus, Earth, and Mars, and they either have no atmospheres or fairly thin atmospheres. We then reach the asteroid belt, though really the asteroid belt isn't like some kind of region where all the asteroids sort of congregate. They actually kind of move around the solar system. It's just they spend the majority of their time in the asteroid belt. They'll move beyond Jupiter and inside the orbits of Earth and Mars. Then as we go further out, we have Jupiter, Saturn, Uranus, and Neptune. Those are all called the sort of the gas giants, with Uranus and Neptune sort of sometimes called the ice giants. And these are much, much larger worlds, and they're kind of mostly gas, with some debate as to whether they really have even any sort of solid surface at their center. Beyond that, we have what's termed the Kuiper Belt. This is sort of where we have things like Pluto. Pluto used to be called a planet until it was realized it was much more like other objects in the Kuiper Belt, and perhaps the largest of them. And to kind of give that a little bit of context, when Ceres was first discovered, that's the largest of the asteroids, it was also termed a planet. So we had the planet Ceres for quite a few years before it was realized that that was also just a bit more like one of the asteroids which are kind of within the solar system, just the largest of them. So looking at the nearest object we can see, we have the moon. You can see it actually sort of some detail with binoculars, but to really see the craters in detail, you need a telescope. But one thing I would point out, the absolute worst time to look at the moon is full moon. You can see the seas, which are just dried up. They're basically cooled off sort of lakes of lava. But because the sun is shining straight down on the moon's surface relative to where we're looking at it, you don't really see much detail. As soon as we go away from full moon, you can start to see the shadows, and that brings out detail in the craters, particularly near this line, which is called the terminator, which is the difference between the dark and the light side of the moon, where you can see the most detail as that moves across the surface. Moving beyond into the wider solar system, probably the most interesting planets to observe are Mars, Jupiter, and Saturn. These are images taken by Damien Peach. Although they're taken with kind of standard large amateur telescopes, you wouldn't actually see this when looking through a telescope. Basically, because we're sort of looking through the Earth's atmosphere, it's a bit like looking from the bottom of a pond. The atmosphere disturbs the light. It kind of creates turbulence and blurs things. So these have been processed with special techniques, which I'll talk a little bit about later on. But they're perhaps the most interesting objects because Mars has a couple of polar caps, and you see them grow and shrink over an orbit. It also has clouds and shows frosts. And the markings on its surface, which are created by kind of where the dust lies, they also shift over the years. Jupiter has a very turbulent atmosphere, which is constantly changing and has the great red spots. Also has the four Galilean moons, which we can see. You can even see them with a good pair of binoculars. And then Saturn has its spectacular ring system. Moving beyond our solar system, our star, the Sun, is just one of about 200,000 million stars in our galaxy. On the right here, this is just an artist's impression of our galaxy. We can't view it from the outside because we're within. And that yellow dot there, that's roughly where our sun is within the galaxy. And because we're within the galaxy, when we look at it, we're seeing the disk. And this is what we term the Milky Way in the night sky. It's a sort of a faint sort of milky, what sort of looks like a milky patch, which stretches across the sky and is best seen in summer. It actually looks a lot like kind of some clouds and can easily be mistaken, other than it doesn't move in the same way. It just moves slowly over the sky as the sun rotates. And you can see an image here. This is looking towards the center of the galaxy. And just that milkiness, that light, and that's just all the thousands of millions of stars, which are too faint to see individually, but together their light sort of grows together. And the darker patches, that isn't an absence of stars. That's dust clouds within the galaxy, and the dust blocks the light from more distant stars. Moving on to what we can see within the galaxy, um, there's a good number of stars which are born in star clusters. We have up here to the left M45, the Pleiades, also known as the Seven Sisters. You can actually see that with your unaided eye. And you'll see between about 5 and 7 stars, though with my eyesight now, I struggle to see much without my glasses. Then we have another famous one and very beautiful one, the double cluster in Perseus. Both of these are what are termed open clusters. As stars form, most of the clusters dissipate quite quickly. The Pleiades is about 125 million years old, and probably a lot of the clusters have just sort of evaporated. The stars have wandered off within 100 million years, with a few clusters lasting a few 100 million years. But then we also get clusters called globular clusters, and there are fewer of these, and these are much larger. These typically have a few hundred thousand stars and are sort of globule shaped. And we still don't fully understand how they form, though one theory is that they may be the cause of other galaxies which the Milky Way has absorbed over its history. These two here, these were taken with my tiny little dwarf smart telescope, as well as several of the others, which I'll be showing tonight, to give you an idea of what's sort of possible with today's technology. We also have nebulae. within the galaxy. Stars form from nebulae when they collapse, and actually these two here, this IC1396 and the Orion Nebula, these are where stars are forming, and it's the hot young stars which are causing the nebula to illuminate and glow. And that pink colour comes from hydrogen, because that's the colour which hydrogen gives out when it's sort of excited. And all these sort of darker patches, these are all to do with, again, dust within around the nebula and just blocking the light. Then we've got the two on the right here, the Veil Nebula and the Ring Nebula, and these are the opposite ends of a star life. The Veil Nebula was created when a massive star exploded, going supernova about 10,000 years ago. And what we're seeing here is the material which has been thrown out when the star exploded, which is gradually moving away. And then beneath that, we have the Ring Nebula, which is the M57 in the constellation of Lyra. This is what happens to low and medium mass stars, and this is what our sun will end up like. What happens is the star will eventually use up its fuel, it will expand into a red giant, and eventually throw off its outer layers. And what we're seeing here is the star which has thrown off its outer layers, and this will last for a few tens of thousands of years. They're termed planetary nebula, but really they have nothing to do with planets. It's just in early telescopes, they sort of gave a sort of an appearance of how a planet might look in the telescope. And right in the middle, you're left with a white dwarf, which is just the core of the star once it's died, which very, very slowly cools down. Beyond our galaxy, galaxies tend to clump together in groups. We're part of what's termed the local group, which has about 20 to 30 galaxies in it. The largest galaxies are our own Milky Way, the Andromeda Galaxy, and M33. The Andromeda Galaxy is actually the furthest object you can see with your eye. On a sort of good dark night, you'll be able to see that, or if not with binoculars, but this is about 2 to 2.5 million light years away. So the light you are seeing left that galaxy about 2 to 2.5 million years ago. Going further afield, galaxies kind of group together into larger and larger clusters, and you get sort of these superclusters. Here's just what's termed Markarian's chain. It's a group of large galaxies together. And as we go out into the universe is understood to have been formed in the Big Bang about 13.8 thousand million years ago. Now, in the universe, we can see there are about a million galaxies, which is somewhat sort of mind-numbing. But also, that's just the galaxies we can see. Because the universe is only 13.8 thousand million years old, anything which is beyond the distance where light hasn't had the chance to reach us, we can't see. So as the universe ages, we can see further and further and more and more. So that finishes my introduction to astronomy. I'm then just going to talk a little bit about telescopes and imaging. So the traditional types of telescopes are refractors and reflectors. Refractors use lenses to focus the light, and reflectors use mirrors to focus the light instead. And you can kind of see an illustration of how they work on the right, and then these are just examples on the left. Reflectors tend to be cheaper for a large telescope than refractors because they're easier to make. In fact, a number of modern telescopes use a combination of lenses and mirrors, and that's because it has the advantage you can kind of fold the light path to make the telescope more compact and easier to transport. But even so, binoculars are actually a really great way to start. That's how I started. You can actually see star clusters, nebulae. If you've got a good tripod, that'll also help sort of to see, and you can see the moons going around Jupiter. However, in the past few years, there's been quite a revolution of what's termed smart telescopes. What these do, these combine a small telescope, a camera, and a robotic mount for pointing. And they're an excellent way to get into astronomy. They cost typically a few £100s. You can get them for a few thousand, but I'd sort of recommend if anyone's interested start with one of sort of the smaller, cheaper ones, because actually you can get a lot of what you might do with the larger telescopes, you can actually do with the small ones. The one thing to note, though, these smart telescopes are really designed for what's called deep sky imaging. This is observing nebulae, clusters, and galaxies. They can also do the full disk of the sun and moon, but what they really don't do well is planets and close-ups of the sun and moon. For those, what you need is a large telescope with a large lens because that's what provides the resolution. And you also need a long focal length. So these aren't really designed for doing that kind of imaging. So if you want to see the planets and the sun and the moon, a traditional telescope is typically the sort of better way to look. And of course, noting that anything to look at the sun, it has to have a sun filter. So although some of these can observe the sun, you have to put a filter in front of them. Otherwise, they'd ruin the lens. And if you actually look through a telescope directly at the sun without any filtering, then you'd ruin your eye. Um, in case people want to go back and have a look at the recording, or if I share slides, then I thought I'd just give a quick list of the smart telescopes and some UK retailers. There are others out there, but these are ones who I've known and used. The Dwarf Labs and ZWO, those are probably the most popular ones, and those are the ones which cost a few £100 and are designed, these all are designed to be sort of relatively easy to use, and you can control them from your phone. So to record the night sky, there's a few different ways we can do it. I still do a bit of sketching at the eyepiece. This is just a crude sketch which I have here of the planet Mars. You can also attach smartphones and DSLRs. Here's an attachment you can have for attaching a smartphone to a telescope, though you will be limited in the sort of detail you can see just by attaching a smartphone to a telescope. Dedicated astronomy cameras will give a much better image. But the smart telescope is a kind of really nice way to integrate everything together. Then you don't have to get a telescope. You don't have to sort of then combine that with a mount and get the camera on and get it all working together. It's all just integrated. You still have to do a little bit of setup, but they're designed to be easy and controlled through your sort of phone or your or a tablet. As I was mentioning with sort of what you might see with smart telescopes, sort of deep sky objects versus planets, there's also two different types of imaging and how they are done. And although you can get some good all-round telescopes, like for example, what's termed an 8-inch Schmidt-Cassegrain, which is a fairly sizable telescope, for actually doing deep sky and planetary imaging, they need to be set up differently. So if I start with deep sky imaging, this is where you image nebulae, galaxies and clusters. These objects are faint, so they need long exposures, typically an absolute minimum of a few minutes, but more typically several hours. And so to observe them, the telescope needs to track the target well. And typically what you'll do is you'll take multiple short exposures from, say, 15 minutes to 2 minutes and then add them together. What we have here is this is an image of the galaxy M33. The top one is just a single unprocessed image of 60 seconds with my Dwarf 3 smart telescope. What the software in the smart telescope then does is it applies calibrations, which are dark, bias, and flat frames. The dark frame is because any camera will have what's called this thermal noise, which is just because it's at a certain temperature, the electrons in the chip will be moving around, and some of them will jump into the charge wells, which are used for making the image. And by taking what's termed a dark frame, you can subtract that off. But the smart telescope does that for you. And similarly, a bias frame is to do with readout noise. And this is all because they're very faint objects. You need to sort of maximize the signal you're getting. And also have what's termed a flat frame. With a telescope, it doesn't evenly illuminate a sensor or even in the old days camera film. What it does, the middle will tend to be brighter than the edges. And what a flat frame does is it just corrects for that. It adjusts it to make the image sort of nice and sort of flat. And then once you've got these calibrated images, then they're aligned and stacked. And that's what smart telescopes do. You can also do that on sort of computers. There's software out there to do that for you. And then you can have a bit of post-processing where you might stretch the image to bring out the contrast and faint details and sometimes sharpen it. So what you can see here is this is where I've combined a lot of 60-second exposures together to give a 6-hour image of M33 where you can see a lot more detail. The other type of imaging is planetary imaging, which also includes the sun and moon. These objects are bright, so you don't need long exposures, but you do need large telescopes because the physics of optics means that the resolution is limited by the aperture. So the larger the lens or the mirror, the more detail you'll see. However, there's another factor, and that's, as I was mentioning earlier, we're looking through the Earth's atmosphere, so fine detail is blurred out. So what's happened in recent sort of past couple of decades, a technique called lucky imaging has been developed. And what this does is this takes short videos of up to a few minutes in time, and each of those, basically you've got very short exposures which create that video. What that does, that freezes out the Earth's atmosphere in each of the images. So they're very short exposures. So the atmosphere may be bubbling away, but you're just seeing individual slices of that. The software will select the clearest of the images and then align the individual frames, sometimes do a little bit of manipulation of the frames, and then combine them. And then software can sharpen the image. And that's what's produced at the end of it. This is by Martin Lewis using a 40 centimeter aperture telescope. If you were just looking through it, you'd see the great red spots. You might just see a little bit of detail around, but you'd see none of this structure because it would just all be blurred out by the motion in the atmosphere. Just to give you some ideas of image processing software, there's some of it which is free, like Cyril, others like PixInsight, which is paid for. These are kind of all-round processing software, but for planetary imaging, where you take the videos, there's AutoStackert and Registax, and thankfully those are both free. So now just moving on to what can be observed in the sky. There are some websites which can kind of advise you on what's up in the sky and what to see, like inthesky.org and the Sky Live. But what there's also very usefully is planetarium software. What this will do is you'll either enter the coordinates for where you are on the Earth, or it will be able to get them from your smartphone or phone or computer. And then for any date or time, it will show you the night sky where you are. And you can zoom in and zoom out to look at details. You can see what's sort of visible. It often it will also sort of show some suggestions. Quite a lot of smart telescopes come with this kind of planetarium software built into the apps which come with them, so which you use from your phone or tablet. And here you can just see, for example, this is using Starry Night, which I use, but there's Stellarium, which is pretty much almost as good, but it's free. And what you can see is Orion, you can see Jupiter up there, the moon, and it just allows you to see what there is, and you get direction so you can see that south. Other websites are also important. Unfortunately, in the UK, we get very unpredictable weather and also get some long spells of rainy weather like we've had recently. But there are some websites which are specifically designed to help astronomers. So we've got Clear Outside and Meteor Blue. And what they do is they don't just show you kind of the forecast cloud coverage, but they'll show you different sort of heights of cloud, what the seeing is like, whether there's kind of rain or some mist around and wind direction and strength. So a lot of this you can get from other websites, but it all just kind of puts it in a sort of very kind of easy to read format to see what's happening. So you can see total cloud cover at the top and then whether it's low or high cloud. So low cloud might be patchy, which you might be able to see some things between. There are also forums like Cloudy Nights and Stargazers Lounge, as well as for asking advice. Also very good for looking at reviews where people write up different equipment. And there's organisations. There's the British Astronomical Association and the Society for Popular Astronomy. And there's also a good number of local organisations around the country. Now moving on to the final bit, where I'll just discuss a bit about computing for astronomical research. So computers in astronomy very originally referred to people. It was a job title. And probably the most famous are the Harvard computers, who are a team of women who devised the stellar classification system back in the early 1900s. And they worked at Harvard College. And what they did is they analysed tens of thousands of spectra. What a spectrum is, it's a bit like a rainbow. You stretch out the light from the star, but you stretch it out sort of in very broadly and in high resolution. And what you'll do is you'll often see a series of dark lines and sometimes some bright lines in the spectrum. And that will tell you about what the star's made from, what molecules and atoms, but also things about temperature and pressure. So it's very useful and sort of diagnostic, which is used in astronomical research. But it all started, and we still use the stellar classification system devised by these Harvard computers. However, it is the advent of electronic computers that's really revolutionized astronomy, as well as many other parts of the world we live in, whether it's predicting the positions of bodies or controlling telescopes, but also with sort of simulations for stars, planets, and the universe on supercomputers. Now, many professional astronomers write their own software, so that's what I spend a lot of my day doing. And typically now, a lot of people are writing in Python and also AstroPy, which is a very sort of useful module with with functions designed to help with sort of astronomy research. There's actually also still a lot of Fortran program going on, as well as C and C++. And there's a version of SQL called ADQL, which is Astronomical Data Query Language, which is based on SQL, but has a few extra functions which are very useful for sort of doing with astronomy. There is some software written for professional astronomers. There's something called TopCat, which was created by someone in Bristol. And that's very useful for creating plots of data and analysing tables. And also there's Aladdin. And what this does, this sort of displays sky surveys and catalogues on a computer. And it isn't quite like sort of planetarium software, but it allows you to sort of look at lots of different sort of images taken with different telescopes, whether it's in the optical, but also infrared, X-rays, and radio. So you can really sort of, it's a very useful tool for sort of getting to know sort of if you want to see different aspects of a particular object. On websites, perhaps one of the most useful ones is something called Simbad, which is run by the University of Strasbourg. They also are responsible for Aladdin, so you may see some theme going on there, and they have some others there, Vizier as well. What Simbad is, it's a database of astronomical objects which you can access online, which is really very handy. And now just going to move on to one of my colleagues, Dr. Neil Lewis, I share an office with at Exeter. I'm an observer and Neil does simulations. So he's kindly given me a bit of information which I put together in some slides. So with the simulations, this is kind of about simulating fluids, whether it's geophysical or astrophysical. And what happens is an atmosphere or perhaps the interior of a star is divided into a grid of small boxes. At each point, they apply the equations of fluid motion and sort of just move it forward in time points, and they'll do things like predict quantities like temperature and velocity and pressure. Where the flow becomes very turbulent, a lot of fine structure is needed, and the high resolution needs a very powerful computer, and then they'll kind of move on to supercomputers. So here's an example, which is a simulation of the sun. This is a very modern one. You can see a disk of the sun there and a zoom in here. Even this using what was the world's fastest supercomputer, Fugaku, back in 2021. This grid is just 384 by 1536 by 4608, which comes up to just under 3 billion grid points. But doing all the sort of physics calculations and incrementing time points, that still, for this simulation, took 40,000 CPUs for 20 days. Here's one of Neil's actual simulations, and hopefully you'll see this video running. Um, this is a model of a star. This is just a single frame from that, and you've got the star sort of on the outside, and then you might just see it's kind of got a little bit of a cutaway to see a bit of what's going on the inside. And this just shows the turbulence in there. And this simulation used 2,000 CPUs for 15 days on the Cosma 8 high-performance computer in Durham. And this was written with a combination of Python and C. But it kind of shows the kind of things which can be done sort of with the sort of modern computers. A decade or two ago, a lot of what the simulations would be 1D, then get to 2D, and now we're sort of at the point where we can do 3D and evolve them over time. What I do in my research, as I mentioned at the start, is I'm involved in star formation and young stars, and I'm an observer. So what I typically do is I'm using sort of publicly available surveys, which are available from space and ground-based telescopes. One of the ones I use most commonly is Gaia. And what this is a space telescope for determining distance. And the way it does that is Gaia is kind of close to Earth, but because of that, the Earth orbits the sun. And as the Earth orbits the sun, it gives you sort of one side of a right angled triangle. And just a very small side, but you see a tiny, tiny wobble in the stars over the course of a year. And by measuring the positions very precisely, Gaia can work out the distances to nearby stars. I also use WISE, which is an infrared space telescope, and also the Very Large Telescope, which is a ground-based telescope with an 8-meter mirror. What I tend to do is I'll combine the data from multiple different surveys and then compare it to models. I'm also part of a team using a new spectrograph called WEAVE on the William Herschel telescope. A spectrograph is Okay, so it just creates a spectrum, but a very high resolution spectrum. And I'm using that to investigate young stars, and that's here. Sadly I don't get to visit because everything's done remotely these days. I just submit what observations we're going to sort of do, and over the next about 5 years, we hope that they'll be observing about 50,000 candidate young stars, which we put together. For my PhD, I built a machine learning tool for finding young stars. I built this in Python with NumPy and AstroPy, and this uses what's termed a naive Bayes classifier, which is just a sort of, it's kind of simple statistical approach, but it has a particular advantage in that it's not a black box like, say, a neural net is. And what that means is you can look at the output results, which are sort of classification probabilities, trace it back through the mathematics to the input features to actually understand why each classification was made. I've applied the classifier to a nearby region of the Milky Way, about 2,000 parsecs out from the sun, which is about 7,000 light years. And to see where that is in the scale of the galaxy, this is our sun, and that's about that white circle is about 2,000 parsecs from the sun. And within that, I'm just looking for candidate young stars. So if we look on the night sky, this is just kind of a full view of the sky if you weren't looking at one hemisphere, but just sort of stretched out, a bit like you have maps of a sphere spread out. And what we have here is this is the galaxy, with the sort of the brighter bits are sort of all the stars, the yellow and darker bits are where there's dust blocking the more distant stars. And then this is where I do my survey. So this is where I combine the results from multiple surveys to find candidate young stars. And to try and explain this a bit and how the classifier works, if I take that sort of region of the sky and just stretch it out flat, that's what we'd have here. So that's this bit just stretched out sort of flat. But what this is the inputs to the classifier. So the classifier takes 5 inputs, and each of those inputs has about 10 million stars in it. And what we're seeing here, the top one, is how variable is the star? How much does it vary sort of over time? And how much does its brightness change? And where it's darker, that means that there are more stars which are varying. And varying variable stars are often likely to be young stars. So that's one of the inputs. So there's these dark features, which are where we're finding more variable stars. Beneath that, this is WISE. So this is looking at the mid-infrared. And again, where it's darker, the stars there are showing features in infrared which are typical of young stars. Young stars have a disk around them which accretes onto them, and that disk glows in the infrared. Beneath that, in the middle, we have what's termed H-K, but really this is just near infrared. This can be taken from the ground, and again we see some very similar structures, though slightly different, and those darker bits are where we're finding young stars. Next is what's termed a H-alpha excess. If you remember that pink glow from the nebulae, young stars also have a pink glow from the hydrogen, and that's what we're seeing here. And then finally, a weak feature, what's termed isochronal age. What this does is this looks at how bright the star and what its colour is. And from that, we can deduce a likelihood of how likely it is to be young. But these are all the sort of features which go into the classifier. And then the classifier combines them. And then I come up with a set of about 6,500 out of 10 million sources, which are high probability young stars. And this here is just the same sort of stretched plot as sort of, oops, these were on the sky, stretched, that just stretched out flat, like we see there. But that's now just showing the candidate young stars. Beneath that is exactly the same, but I've just highlighted where we have known young stars and star-forming regions, young clusters, and the fact that these are lining up gives us confidence that a classifier works at some level. And the bottom plot, I've just replaced the vertical axis, because this is like we're looking up on the sky, but I've taken that away and replaced it with distance, so we can see they're also grouping together in distance as well. So just to summarise, there's a lot to see in the night sky, and you can even do it from light polluted cities. And the smart telescopes can be quite good for cutting through light pollution, and you can see the moon and planets even with light pollution. Binoculars are a good way to start. Smart telescopes are a great way for getting images of nebulae, galaxies, and star clusters, while traditional telescopes are better for planets. There are websites to tell you what to see and planetary software to tell you where to look, as well as national organisations and local societies to help you get started. And research astronomers spend a lot of our time writing computer code for simulations and analysing data. Thank you.
Great, thank you very much. So, if we can maybe start with some questions in the room. Anybody got any questions in the room for Andy? Anybody want to kick off? Yes, Ed.
I have two. Can I use the software that tells me where things are to feed into a smart telescope?
Yes and no. What you tend to have is each smart telescope will come with its own software, and typically it will have some planetarium software. And with that, you can then tell it where to point. You can get other software and planetarium software, but often it doesn't integrate well with a smart telescope. There can be ways of doing it and the ways to integrate it with traditional telescopes. But to be honest, the software which comes with smart telescopes is usually good enough. A lot of them, if I go back to, no, not that one, but here, Stellarium, which is the free one. Actually, a lot of the smart telescopes come with their own version of Stellarium. It's a little bit different to the sort of standard free one, but they integrate it with it. And then with that, you can point the telescope, you can find a target on the planetarium software and then tell the smart telescope to go there, and it'll automatically go and find the object.
Oh, thank you. Can I ask one more while
Yeah,
I'm on?
please do.
Some of my research used to be in image processing, and what am I right in thinking that some of the ways we generate magnetic images, say in medical MRIs, is that related to the same stuff that I'm looking at now?
Not. There are ways in which it is used, but I don't think. Basically, for the MRIs, and I forget exactly how it's done, is done in a certain way, whereas the kind of normal astronomical images are done by kind of just sort of enhancing the image, either stretching the image or trying to sort of look at related pixels. But the way MRI imaging works is used in to combine results from spectroscopy to create images of stars. Normally, a star is far too small for even the largest telescope to be able to see its surface. But one of the things they can do is by looking at a spectrum and how it evolves over time, you can essentially see how the spectrum changes as the star rotates. And you'll have star spots coming on off and off the surface. And I believe that the same techniques used in MRI were then used to take that data to then reconstruct images of stellar surfaces.
Thank you. I feel like I've just had my understanding broadened. That's great. Thank you. Great talk.
Thanks very much.
Okay, we've got one hand up in the. I'm just going to go online.
Yeah, that's fine. Yeah.
Okay. All
right.
Yes, I can hear. Yeah, I need to know about how to capture the star tail on that. Is there a specific way to capture on that the capture monitor on that the star tails?
Do you mean so star trails? You mean sort of a bit like kind of where I probably don't have something to hand, but where you kind of you see the stars which are kind of curved around in the sky. So
not a cow, that's a tail, just like a Halley's.
So I'm not quite sure if I understand, but there is something called star trails, and what you do with a star trail is basically you typically have a wide field view camera, but it doesn't track the stars, it just points, and therefore as the Earth rotates, you get trailed. Sort of the light from the star is then trailed across the image, and you get these trails on the sky.
All right, fine. Okay.
Okay. Did that answer your question, Raj? Okay.
Or
what is that? I couldn't hear you.
Yeah.
That's fine. Yeah, that's fine.
Yeah. Otherwise, you have things
answer.
like meteors, which you also want a wide angle camera for, and you just point at the sky and sort of take an image sort of every few minutes, but lasting for say 30 seconds or a minute, and then you can kind of capture a meteor flying across.
Fine, right. Thank you.
Thank you. Come back in the room then. There's a couple of questions.
Just wondering, Andy, has AI-enabled functionality got into any of this software yet, or is that yet to come?
Yes and no. I believe there's a bit of AI functionality in sort of some of the software for choosing processing options within sort of some of the sort of smart telescope image processing. Where it's frowned upon and not really used is kind of generative AI with images. Every sort of few days, I see someone who's taken an image with a small telescope, given it to, say, ChatGPT or one of the others, and said, "Can you improve this for me?" And they get a new image out. But that image isn't the one they put in, really, because what the generative AI will do is it will use it as kind of inspiration and then create a new image based on its training of what it might expect to see.
Yeah, I could see that would potentially be an issue when I saw some of the earlier images, thinking, "Oh, somebody's going to take a shot."
Yeah, I see. What's quite interesting
with the strap line.
What's quite interesting is you occasionally see some. I'll just see if I can find an example. Probably not good example, but with galaxies, and you'll see they've got this really great image of a galaxy with spiral arms, and if you compare it to another image, there's an extra spiral arm in there, or some stars which aren't real. And so there's sometimes, quite often, there's ways you can just kind of tell, okay, yeah, that one's not an actual proper image. It's just being sort of AI created kind of thing.
And I'm going to ask you another one, which is it's nothing to do with software. This is, so you're tracking new stars.
Yeah? Yes.
Why? So, I mean, what, and I'm not being, I guess, what are they a risk? Are they, what,
no,
how does it fit in the equation?
It's really to understand where we came from. And I think, although there are we do learn things through astronomy which are applicable to the everyday world, various sort of techniques which are developed. But actually, for me, it's a lot about kind of the wow factor of understanding where we are in the universe. And a lot of understanding young stars is understanding our place in the universe. So when our sun and planets formed, that happened about 4,500 million years ago. So we don't really see how that happened, but we can see the kind of things which caused that by looking at other stars. And star formation is a long process. We tend to see kind of different stars in different stages. The stars which I look at are around about 2 million to 10 million years old. And that might sound old, but that's very, very young for a star. And it's not even a proper star at that point. A star's a proper star when it starts to fuse hydrogen in its core. But what this does, this gives a perspective on kind of our place in the universe and sort of how sort of it's kind of a bit like we're tiny, but it's also kind of interesting to learn how the universe evolved and sort of nature, that kind of thing.
Thank you.
Thank you. We'll go back online again. Richard Gosling, you got your hand up. You want to go off speaker? Richard,
yes. Hello there. I'm just curious, given that obviously one of the restrictions with sort of observing is down to Earth's atmosphere, and obviously that's why we've launched telescopes into space and so on. But the bandwidth to those is obviously very limited. I'm just wondering with the companies like SpaceX who are planning on putting like data centers into space and all that kind of thing, whether that will obviously make the opportunities of viewing those remote telescopes more available to the general public, because obviously they'll be able to beam to the servers that are already orbiting, and then that will have a much higher bandwidth connection back down to Earth. And so potentially we could have like live streams from remote telescopes, couldn't we?
It has an effect, but probably not in the way which you think. So for the space telescopes, they actually already have very high bandwidth.
Mm-hmm.
So the actual sort of sending back of data, but typically the space telescope usage and also ground-based telescope will be booked up months in advance.
Yeah.
And what they have is they have teams of astronomers who assess, basically, as an astronomer myself, what I do is I put a case together for making an observation, and then that would go off to a team who'd then review it, and they'll decide which ones are used and which ones aren't, because all of the telescopes are basically oversubscribed.
Yes.
But where it does come in, particularly with, at the moment, Starlink, there are so many satellites that they're starting to affect amateurs, but also professionals, because they reflect sunlight and you can then see them. They become as streaks in the image and they can ruin observations or cause false alarms. And if the data centers were to go up, there's just so many of them that you'd get all these points of light. It would cause a lot of havoc. Though I suspect the data centers probably won't go ahead because of the cost of putting them up there. And actually, for example, it's quite difficult to cool something in space. So you might think being in space would help with the cooling, but actually it doesn't. On one side, you're being superheated by the sun, and the other side, you've got sort of just the cool sky, the cool kind of basically the rest of the universe to cool off, but you haven't got any atmosphere or fluid against it. So you've just got sort of giving out radiation to cool it down. So it's actually quite hard to cool things in space. So
Okay. So the recent filing by SpaceX to the FAA to launch 1 million satellites for this provision is not necessarily welcome news for yourself.
No, it's basically, even with Starlink, a number of sort of astronomy organizations have put in sort of complaints. They've tried to redesign some of the Starlinks, reduce them, but what you'll see these chains of satellites going across the sky, and of course it's just building up and building up over the years.
More interference, yeah. Okay,
yeah. What you have with the smart telescopes is, and with others, every few images you'll get a streak across it, which will be a satellite. And what they do is they've got algorithms to try and identify that and then throw away the image.
Okay, thank you.
You're welcome.
Thank you. Another question in the room? Dave, did you have your hand up first or no?
I was going to, Sharon.
Sharon's asked the same question.
Yes, similar.
Oh, look at you joined it there. DC? Yes, sir.
Yes, my question is a more general one about the formation of this wonderful cosmos that at some stage in the process of aging from the beginning of the universe, matter started aggregating, but in different ways, making small dense clumps or large open clusters and many other things in between. I just wondered if there had been any experiments, either thought experiments or with a possibility of future real experiments in space-type conditions, low vacuum, low gravity, of seeing how materials, seeing if one could reproduce this behavior from stardust effectively, to see if theories about these different kinds of aggregation might be reflected in practice.
There's kind of a bit of that. There's a lot of computer simulations, and what they do is they put in the physics and then try and simulate what happens in the early universe and then evolve them over time to see which simulations then come out to look in the right level of clumpiness to explain the universe which we do see. We can't really aggregate things together enough to simulate that over time. We do have things like the Large Hadron Collider and other particle accelerators, which simulate the very early conditions in the universe. But the sort of process which went on in the first second of the Big Bang, things were very, very hot and dense. But then up to about 300,000 years, the universe was just kind of what's termed ionized. The atoms, there was just pretty much hydrogen, a bit of helium and electrons, but everything was kind of separated. And after that, everything sort of separated out and things became, sorry, not separated, but atoms and molecules, the electrons combined, created neutral atoms. And then we got the first light, which we can see, which is termed the microwave background. Now, what astronomers can do is they look at the microwave background, and by looking at its shape and its lumpiness, it gives a good indication of how lumpy the universe was at about 300,000 years old, which is very, very young. We then have a gap where we don't really see much, and then we've got the James Webb Space Telescope, which is looking at the infrared universe and can see much further back in time. It can't see back to the cosmic microwave background, but it can see to, say, 1 billion years to a few 100 million years after the Big Bang, and see how the clumpy the universe is, how the first galaxies were forming. And they're just starting to get some results on there to give indications which will help tie down which models we have are right, or which ones probably are just completely wrong because they don't simulate it, but just kind of narrow down our understanding. And a lot of this comes down to dark matter as well, because when the equations of physics are kind of evolved, just with the ordinary matter we see, one of the problems is the universe doesn't end up lumpy enough. We don't get galaxies forming. It's only when they add the dark matter that we start to see sufficient mass and sufficient lumpiness to get galaxies and then stars forming.
Yeah. If I'm thinking as a writer, okay, and I want to have characters in this galaxy, right? If I then decide that how do I think that this galaxy, they have history of their own that I think may have existed prior to discovering this galaxy, maybe millions of light bangs years away, then would that then affect the simulation? Because then we'll not get a true reflection of what we're trying to accomplish from that point of view. Is there any some kind of sensical notion you can draw out of that nonsense?
It depends. If you're talking about kind of other life which might be evolving in the universe, then that's unlikely to have a big effect on the large scale structure. And particularly, I mean, it seems very likely that life is elsewhere in the universe. Most of it's probably very simple. Even microbes are sort of fairly complex. But for actually sort of changing something like a galaxy is very, very big. So our galaxy is around about 100,000 light years across and has around, well, it's thought between 100,000 and 400,000 million stars. So it's very big, and there's a lot of kind of everything we see indicates that it's just following sort of laws of physics, and you can wind things back and see how galaxies evolve and change. Where things tend to get a little bit tricky is going from the very early universe to, say, the first billion years, and that's where we really don't understand enough about the physics of what's going on and what the nature of the dark matter might be, which is kind of influencing the gas which is in the early universe.
But could it actually have a history of itself that is repeating in its generation by its own formation?
It depends. So I think there used to be some theories around sort of whether the universe might be going through a cycle of a big bang and a big crunch.
Right.
We can't sort of say that doesn't happen, because anything would be sort of, any knowledge of it essentially gets wiped out in a big crunch. Though at the moment, what it looks as though is the universe expands and is just kind of at around about the point where it just carries on expanding without quite collapsing down together, though it's very tricky to make precise measurements. The other thing to note is when the Big Bang happened, it isn't sort of stars and gas exploding out into space.
Mm-hmm.
Space and time are created at the same time. And the kind of way to think about it is rather than having a three-dimensional universe, if you imagine a two-dimensional universe, which is the surface of a balloon. The Big Bang is where the moon is deflated, and then you blow the balloon up by blowing air into it. The surface of the balloon expands, and that surface is space. So if you drew galaxies on it, the galaxies would get further apart because the balloon surface is stretching. And that's essentially what happens with space. The space itself is expanding and getting larger. So it isn't that the objects are traveling through space to get further away.
It's very nice.
Gosh, that's something to contemplate.
Yeah. Thanks for that.
Yes, yes, it gets a bit mind-numbing at times.
Yeah. Ashok's asked a question in the chat. I don't know, Ashok, if you want to come on speaker, or shall I ask the question for you? Shall I ask the question, Ashok?
Hi. Yes, it's actually a similar question to the one already asked from the satellites in space. So I guess from what you said, the astronomical sites in on ground base won't be transmitting live images um, because of the cost, I guess, and time slices allocated. Is that true?
It's not really about live images. So with there's a number of different types of sort of telescope. The sort of more traditional type will take an observation and it will stare at an object for, say, an hour. And during that time, that light will be building up on the sensor. So there won't be a live image to view because the sensor is occupied with kind of building up the image. And once the hour's up, it will then take that, download that from the imaging chip into the memory of which is on board with the telescope. A lot of the modern telescopes will do a bit of image processing on it and then send it back to the ground. There's some, for example, like Gaia, which does the measurements of distances, which does an amount of sort of processing within the telescope rather than sending all the data back because it's such a vast amount of data. And what that does, it does a bit of processing and then kind of sends back sort of summary data to the ground for further processing. But also, just to give a bit of an idea in some of the volumes, there's I'm involved a little bit with a new telescope called LSST, which is a Large Synoptic Survey Telescope, and also known as the Vera-Rubin Telescope. And that surveys the entire sky in high resolution, roughly every 3 nights, and in different colours. And that's generating petabytes of data.
All right.
So they've got a big kind of problem with trying just simply to work out what to store and how to process it. They've all got sort of pipelines for doing it, but it's kind of trying to get everything to work as efficiently as possible. And a similar one is the Square Kilometre Array, which is a set of radio telescopes being built whose total surface area is 1 kilometre. Sorry, 1 square kilometre, but the amount of processing which has to go on through all the different telescopes combined is equivalent to, I think it's roughly speaking, the entire internet traffic of the world every day is the amount of processing it's got to deal with. So they're spending, I think, something like $300 million just on the computers to try and sort of do the initial analysis and then store the sort of key data which they need.
It's an electricity bill.
Yeah, it's a huge cost. I think it's around about $1 billion, the total project cost.
I hope the energy is coming from the sun.
Yes. Yeah, if you can get the solar panel. I mean, it's being built in sort of, I think some of it's in the Australian desert and some of it's in South Africa. So they're probably very good places if they can get the solar panels set up to power it.
Wow. Fantastic. Any further questions in the room? Yes, sir. Back.
Yeah, so obviously the sensors are getting better, the computing power is getting better. Is it all about effectively refining and getting a better view of what we already knew? Or have we discovered things that actually has completely changed the view of the universe simply because we can see better than we used to be able to?
And that's a very good question. And it is a kind of, yes, very much. Telescopes and detectors are improving. The ones in the visual are getting close to how good they can be, but they're getting larger. And the ones in infrared and ultraviolet are still kind of going through improvements. So the ones in the optical pretty much capture almost every photon of light which can be captured. But even then, larger telescopes are being built. And one of the things which is being done with them is they have what's termed adaptive optics. And the way that works is you fire a laser up into the sky to create an artificial star. Then that's imaged, and computers work out by looking at how it's blurred, how to unblur the image which the telescope sees. And there's a new telescope, which is, unfortunately, some of these don't have very imaginative names, but this is called the Extremely Large Telescope, the ELT, which is in Chile. And this, I think, has something like a 45-meter mirror, and that's just being built. And the thing is, when you have these new telescopes go online, there are almost always new discoveries. Some of it is in areas where we think there's things to be discovered. Sometimes it's just things which no one expects. In the young star work, which I do, we're still learning. So, for example, one of the areas I look at is star spots. We know that young stars are very magnetic and they have a lot of star spots. They're sort of connected, but quite how much we're still working on. Our sun has about 1 to 2% of its surface covered in spots. We think the young stars have 50% or more of their surface covered in spots. James Webb, which was launched, I think, about 2.5 years ago now, that is looking very far into the universe, the infrared, and to the very early universe. And we're starting to see some of the very early galaxies, and we're starting to learn things about those. One thing which is very much not properly understood is what the first stars were like. When the universe was created, it was pretty much hydrogen and helium. Everything we are made of, which isn't hydrogen and helium, so including carbon and oxygen, all was created in the cores of stars. And when those stars die, they throw that material, that carbon, oxygen, all the other elements out into the universe, which then gets formed in the next generation of stars and the stars and planets. What they're sort of just tentatively trying to see with James Webb is whether they can start to see back to those very, very earliest stars, which were just pure hydrogen and helium.
Very good. Thank you.
Is there another question?
Yes, I read recently something about Betelgeuse in Orion.
Yes.
Betelgeuse. I'm not sure what the pronunciation is.
Yeah.
But that it was actually quite an unstable star, not far from the end of its life, and that when it goes out with a huge outburst of energy, that it will make the nighttime seem daylight on Earth. Does that sound plausible to you?
Yes and no. There's a bit of nuance to it. Betelgeuse is approaching the end of its life, but from analysing it, the light and looking at how it's changing and where it is in its life, we think it's probably about 500,000 years before its end. So sadly, it won't be in our lifetime, but it is one of the stars it's more towards the end of its life. It's just stars live so long that when you get towards, it still takes quite a long time to reach that point. But when it does reach the end of its life, Betelgeuse is a very massive star, and that will end in a supernova. And when it does, yes, it will be incredibly bright. It probably won't be quite as bright as the sun, but it will probably be something of the order of similar the brightness to the moon, but as a point source. And actually looking at that might damage your eyes, and it would mean that night wouldn't be as dark. I'm not quite sure if it would be enough to really kind of light it up so we don't see many stars, or just sort of reduce the number because the sky is so bright.
I'm so relieved.
Yeah. I was thinking, oh gosh,
yeah,
is that worth setting it? No.
Yeah.
That's right, fantastic. Any more questions online? Okay, I can't see any more hands up. Anything else that you'd like to ask? Andy? No. Oh, no. That was just Alex saying thank you. Anybody else? Any questions in the room? No. We're again going to just say a big thank you to you.
Thank you very much. And it's been a pleasure. Just a shame I couldn't be there in person.
Yes, it is a shame, but we're ever so grateful for you to dialing in remotely to give us such a wonderful evening of understanding. Certainly, I've learned an awful lot. I normally ask loads of questions, but there's just like so much I don't know. I'm just like listening to see what's actually happening, really. So that's fantastic. I mean, I suppose for me, one thing might be, is there like you mentioned about the software program, just bringing it back to the BCS and computing. Is there like a particular place that specializes in computing for astronomy in terms of if somebody wanted to go and do something themselves? I mean, you provided some links already, which is very helpful, but is there a course, or is there a degree or something, or
it's kind of pretty much, if you do astronomy, you end up doing lots of computing.
Yeah.
Right.
So as an undergraduate, you'll do a bit of computing. If you go on to do a master's or PhD, you do lots and lots of computing, spending almost all your time. I helped teach the second year undergraduate physics lab at Exeter, the astronomy side of it. And basically that is just using Python to analyze images.
Okay.
And that's pretty much, we do get to use the observatory sometimes, so we're hoping we may in the next few weeks, but that's basically taking data, which we then go and process in Python.
Oh, fascinating. Oh, good. Well, there you go. So if anybody fancies it, you know where to contact, and you go to another undergraduate degree in physics stroke astronomy, really. And the other thing, just quickly asking, do you get involved at all with the guys up at Keele?
Strange you should say that. Yes, so they're on part of the team which is using Weave. So we're all part of the same team, sort of looking at young stars. They look at a slightly different aspect. What they're doing is they're looking at what's termed how stars clusters evolve and stars get ejected from clusters. Whereas I'm more interested in whether there's kind of isolated star formation going on, which isn't in clusters.
Gosh, it's like everything else, isn't it? I suppose you've got kind of, absolutely micro sets of understanding within the huger thing, a bigger, amazing, really. But it's great that you're organised. You're not looking at the same thing, isn't it? That's fantastic. Actually,
it's
line up a little bit, really.
Yeah, I'm hoping to get up to Keele sometime, but I'm waiting to see if they can find some money for me to go and give them a talk.
Oh yeah, well, indeed. We've got some colleagues in Keele, so if you do come up after drop us a line, we can pop over and buy you a coffee or something.
It's Nick Wright and Christina who I mostly work with.
Okay, very good. So I think that's it. There's no other questions.